Okay, so last thing I forgot to mention is the Christoffel symbols. So the Christoffel symbols, with respect to a coordinate chart, okay, if we remember, we have this affine connection, which we view it as, we're now viewing it as a map from um, the smooth vector fields over the tangent bundle, smooth sections of the tangent bundle, which are the set of smooth vector fields, cross the set of smooth vector fields. So set of smooth vector fields cross set of smooth vector fields into the set of smooth vector fields. So it takes in two smooth sections of the tangent bundle and outputs a smooth section of the tangent bundle such that it is tensorial, i.e. C infinity M linear in the first argument, and it obeys the Leibniz rule with respect to the second argument. Okay, so um, given this affine connection, then we have then pick a coordinate chart. We're going to have a basis, a frame of the tangent bundle adapted to that coordinate chart. So that's going to give, remember, that's just the coordinate chart gives us essentially a diffeomorphism, but it's a homeomorphism into Rn. And if we just pull back, or essentially push forward under the inverse of the coordinate chart, we push forward the canonical basis vectors, um, um, partial over partial xi, from the image of the coordinate chart back onto the manifold, back onto the tangent space of the manifold, we get a basis for the tangent space of the manifold, partial I. So we have this coordinate vector frame for our tangent bundle, and the point is that we can evaluate the affine connection on basically this coordinate basis. And what we're going to get is d of partial I comma partial j. So that's the directional derivative of the vector field partial j in the direction of the vector field partial I. So that's d of partial I comma partial j. That is equal to some coefficient functions lambda superscript k subscript ij partial subscript k, right? So the sum is over k. Of course, partial k is our coordinate frame. The coefficients of the outputting vector field, the output vector field d of partial I comma partial j, the coefficients with respect to our coordinate vector frame are precisely the Christoffel symbols. Namely, the upper script of the Christoffel symbol, lambda superscript k, is the kth component with respect to that coordinate basis of the directional derivative of partial j in the direction partial I. Okay, so that's lambda superscript k subscript ij. All right. So again, just to repeat that formula, that's d of partial I comma partial j is equal to lambda superscript k subscript ij partial subscript j. Subscript k. Sorry. Let me say it one more time because I got it wrong. D of partial I comma partial j is equal to lambda superscript k subscript ij partial subscript k. All right. And then the one other thing I wanted to mention is, first of all, there are many affine connections that exist on a Riemannian manifold. So, for example, if you embed the manifold into Rn and then use the Euclidean connection on the ambient space Rn and take the directional derivative of a vector field along a curve and then project that directional derivative onto the tangent bundle, onto the tangent space of the manifold, that operator is precise. It obeys the two required laws for the affine connection, so it's automatically an affine connection. So by Whitney embedding, you're guaranteed at least one affine connection. And just due to the fact that there are many Riemannian metrics you can put on a manifold, then depending on the Riemannian metric you can put on a manifold, right? Or I guess yeah, you can always, sorry, not due to the fact that there are many Riemannian metrics. Sorry, due to the fact that there are many possible embeddings. So due to the fact that there are many possible embeddings of the manifold into ambient space, that is going to induce many different notions of a covariant derivative, right? The derivative of the vector field in the ambient space, according to the canonical Euclidean affine connection, and then projecting onto the tangent bundle of the manifold. That process very much so depends on the embedding. And since there are many different ways to embed the manifold, there are obviously going to be many different covariant derivatives you could define on your manifold. Um, However, there's an important property that the affine connection of the covariant derivative, this d, basically this, or it's also sometimes denoted with a grad symbol, um, which I believe is like a nabla symbol. Anyways, it's an upside down triangle. Um, this operator, okay, this affine connection, forms a cone, a convex set, or not a cone, sorry, not a cone, but a convex set. Okay, so it's important to recognize that if you subtract two affine connections, you don't necessarily get an affine connection as a result. And this is just due to the fact that you need to preserve these algebraic properties uh, of C infinity M linearity in the first argument and the Leibniz rule in the second argument. Those properties are not preserved in general if you take the difference of two affine connections. However, if you consider, let's say, k different affine connections, and let's suppose that we have k functions on the manifold, such that the sum of those k functions is identically equal to 1, okay? So this is kind of like a partition of unity, essentially. We take k smooth functions such that their sum is identically equal to 1. Then, if we take the convex combination of those affine connections, the sum of fk nabla k, then what we get is a new affine connection. Okay, so the set of affine connections is convex. It's preserved under convex combinations of affine connections under smooth functions that sum to 1. All right. But it is not linear. So in general, it's not going to be a linear. It's not a linear space. It's not a necessarily a cone, right? Because again, you can add if you add two affine connections, or importantly, if you subtract two affine connections, um, um, the result that you get is no longer necessarily an affine connection. Okay. All right. Thank you for listening.